Hello, my friends. Today we are going to talk about um, Maxwell's third equations. First of all, we need to emphasize that uh, the Maxwell's third equation came from Faraday's law, and Faraday's law uh, is not a complete law. There is a so-called Faraday paradox, which cannot be explained in science. Um, Now, what is Faraday law? Faraday's uh, Faraday law, by Faraday's law, the EMF, which is also called back EMF, is equals to uh, the flux, where flux is the magnetic flux, dT. And here, the EMF here is so-called the electromotive force. Electromotive force. This is also called back EMF. Back EMF. And all these terms is just the terminology of the past. Actually, this one is actually the AC voltage. And on the right side of the equation, we have magnetic flux here, and this one is given by, the flux is given by BA. B is the magnetic field intensity, and A is the area. So this is the Faraday's law. Faraday's law. Now, the purpose of these lectures is to derive Maxwell's third equation out of Faraday's law. And here, if B is constant, then we are going to, the magnetic flux should be given by B times A. But the reality is, uh, the B field, the magnetic field, is not always constant. And in fact, the B field is always not constant. So the magnetic flux will be given by B, which is not constant, and times the area A, and then the area indigo. So this is the right formula, the new formula for the magnetic flux. Uh, Now this is let's label the first equation as equation 1, and we have the second equation here, and we don't need this definition. This definition is not correct if B is a variable. Now, EMF. EMF is um, the actual motive force, which is the voltage um, of a closed loop. So the voltage of a closed loop should be zero, but it also depends on some situation. If you are driving a driver in the loop, then the EMF of the low voltage may not be zero. But in any case, uh, EMF is equals to the loop times EL, the closed loop integral of E, vector E, and um, vector L. According to the Stokes theorem, the loop integral between E and dl can be extended. First, we have to convert them into a vector form. And according to the Stokes theorem, is equal to the surface area. And then the curl of E and dot product of E with the area integral. Yeah. In this case, I also need to convert this into a vector integral. So this is equation number 3. So if we find the derivative of equation 2 with respect to time, so according to 2, um, then the derivative of flux should be given by, and we are going to do some tricks here. In this case, we are going to integrate B field and area, and then we find the time derivative of this integral, So why can't we just find the time derivative first, and then find the area integral? So we can find the area integral first, and then So this is equation 4. According to equation 1, the EMF, which is given by equation 3, and uh, the rate of change of magnetic flux, which is given by equation 4, should be equals. So these two should be equals. So now the inequal size is equal. The inequals should be equal. So we can say that uh, the curl of E in this case should be equal to dB by dt. So this is the Maxwell's flood equation.